Image-based lighting, or IBL for short, is a fantastic modern technique for quickly achieving realistic lighting in a scene. IBL takes real-world color and light intensity information captured in a panoramic image and uses it to illuminate your 3D objects. This image is essentially projected onto the inside of a sphere which encompasses your entire scene. And then the light is cast from this inside surface of the sphere inwards. All right, so here's a quick look at one of these panoramic images, which can be used as an IBL. So we'll talk about these in just a second. This is called an Equirectangular Image. It allows you to get all of the information coming in from all directions mapped onto a single rectangular image. All right, so there's that. Here's another quick look at another equirectangular image. Same deal here. This is 360 degrees of information, but all in a single image. And let's also just take a look in Maya to see what this sphere looks like that I'm talking about. So in Maya here, we've got the first IBL projected onto an actual IBL light source. This is the Arnold Sky Dome light, and so you can see it actually is a sphere, and basically just with the image mapped as a texture onto that sphere, and then you can see here how the light is going to be sent inwards, right, as if it's coming off of the inside surface of this sphere. It is going to be directed at the center of the scene here, or the center of the sphere, and we can actually use this to illuminate this object. So let's actually go ahead, let's get two panels side by side, pull up our render view here. We've got Arnold open, and looking through the perspective camera, let's actually just take a quick render here and see what this looks like. All right, we can see that this cube is basically taking on the color temperature of the environment, and we can clearly see here that it is being illuminated with the same lighting information present in this environment. Right, this angle should really show that off. Right, we see the light coming from the window here, illuminating this face of the cube. And then take a look at the shadows here. They're a bit on the cooler side, kind of matching the rest of the environment. Otherwise they would just be just black. They would be in shadow. But we can see that, well, first of all, they're not entirely black, right? They kind of are taking on a bit of a cooler color. Coming from the cool color temperature of the environment, but also the sides of the object facing away from the window are not perfectly in shadow. There actually is illumination back here, and that's because there actually still is light coming from the back of the room. It's light's coming in from the window, bouncing around at the back of the room here, and it still would be cast onto the subject. All right, so that gives just a quick preview of what image-based lighting is all about. Let's just head back over to Photoshop and take a look at some more details about IBLs. While there are a few alternative ways of capturing IBLs, such as using a mirror ball, the most common method is to generate something like what we see here. And again, this is called an equirectangular image. So this can be achieved in a few different ways. So a method that should be fairly approachable for any artist would be to just take a normal camera and a fairly wide-angle lens and just take many photos of an environment. Now we'll talk about the bracketing going on with these images and how we see like sets of images with different exposures. We'll talk about that in just a second. But first, just notice the fact that the technique actually that was used to create this IBL was just using actually an 18mm lens. So actually not even that wide angle. It's a fairly common focal length on stock DSLR lenses. And we just went around in a circle, camera on a tripod, just panning around and taking just many images at eye level. We'll see some images also being taken from a low angle, with the camera aimed up towards the ceiling, and also at a high angle as well, with the camera pointing down on the scene, just to cover as much of the environment as we can. And then these images would then be stitched together using special software to create this equirectangular image. Another process we can use is actually using a 360-degree camera to take that spherical image all in one shot, right? And that essentially automates the process of stitching together the equirectangular images from component images. And another approach, which is actually kind of interesting to think about, is potentially actually rendering an existing 3D scene using an equirectangular camera. So this is a common setting. You can actually do this in Maya. You can just take any camera and set it to render the scene with an equirectangular projection, and we can actually render a 3D environment and use it as an IBL. So this is an interesting approach, actually. We'll take a look at this in the tutorial for this section and see, another way of potentially approaching creating IBLs, right? So this is a pretty simple scene with some 3D objects and some light sources, and again, just rendered out using equirectangular projection. Now, the images captured will be normal low dynamic range images encoded in the standard sRGB color space. So let's just discuss that for a minute. What exactly sRGB is? So sRGB. What is this color space, right? So sRGB is a non-linear color space designed to encode and display images in a way that's most appropriate for viewing by the human eye. All right, now sRGB images only allow for a limited range of bright to dark areas in an image and can't correctly capture all the light intensity information present in a scene. And this is something that we're going to need in order to correctly illuminate a scene using an image-based light. So before we move on and talk about sRGB and the various details involved here, let's actually just make sure we understand the difference between this high dynamic range image that we're trying to create, right, which contains this full range of light to dark values, and let's just compare that to a low dynamic range image to understand that, those raw photos that we're actually getting from the environment. So this is the IBL. Let's actually switch over just to a low dynamic range version of this same image, and let's add an exposure adjustment here inside of Photoshop. And so I'm going to adjust this exposure value, and let's keep an eye on, let's say, this light area outside the window here, right? So, this kind of makes sense when the image is exposed for the interior of the room. We can't display that level of exposure as well as the correct exposure level for the outside of this environment as well. We can't display all this lighting and color information on a standard sRGB screen, and neither can humans see all of this information. So what we're going to have to do is change the exposure value to darken the entire image such that we become correctly exposed for the details present outside the window. However, as we can see here with this low dynamic range image, well, there there are no more details to be found. This area in these window panes here they've just been crushed up to a just a value of white. There is no detail in visible through the windows. It is gone. It has been destroyed. So it doesn't matter how we adjust this exposure value. We can't find any more details outside the windows. But let's actually take a look over at the high dynamic range image here. This image contains a whole lot more data than we were actually looking at right here. And we can start to see that if we do the same thing here, we go ahead and add an exposure adjustment. And so I'm now going to expose for the exterior of the environment, right? So if I drop that exposure down, we can see that, well, of course, the interior has been darkened quite a bit. But hey, look at that. Because this is a high dynamic range image, and because we used multiple photos taken at different exposures to construct this image, when we drop that exposure down, we can actually start to see some detail from outside the windows here. So yeah, that shows what happens with these bright areas when we adjust the exposure to correctly view them. And the same thing is going to happen with darker areas. Now, to be quite honest, there aren't actually that many super dark areas in this image, but the same sort of thing is going to happen with when we raise the exposure as well. So if we overexpose, maybe, yeah, to be honest, there aren't really that many good examples in this image. Maybe under the table, that would be a good example, where with the exposure set to 0, it's fairly dark. We can't really see what's going on under the table. But when we start to raise the exposure, we can start to see some details in here. Again, because we captured this image using low dynamic range images exposed for, the bright details, the medium details, as well as the dark details as well. So that is precisely why when we were taking a look at this set of images used to create the IBL, that's why we bracketed all our shots. So we can take a look at any image we want. Actually, let's find a shot looking out the window. This shot right here. So we started with just, medium exposure. Sorry, the image is so small and low resolution here, but at a decent, good exposure for the interior of the room. We start with that image, then we overexpose by 1 stop, 2 stops, just revealing any details previously hidden in shadow. Of course, the window is just blown out, just totally blown out. No details being obtained from that bright window area. However, after overexposing by, I just did 2 stops in this case, you could go further. Then we went back and underexposed, again by 1 stop and then 2 stops. And there we go, right? So by dropping the exposure down, we can start to see some of those details come through from outside the window. So it's because we actually used 5 versions for each image here, for each position, or each orientation, I should say, of the camera. We actually bracketed and took 5 images, and then by combining them all into a high dynamic range image, we were able to get all of that lighting, all of those differences in light intensity, all the way from down here where the outside environment is exposed correctly, all the way to maybe up here around +2 EVs, where some of the shadowed areas are more correctly exposed. So that is what we mean by a high dynamic range versus a low dynamic range image. All right, so those low dynamic range images we were looking at, these are all captured and stored in sRGB. They are not appropriate for use as an image-based light. The first problem being the fact that colors in an sRGB image are stored non-linearly. And so what that means actually is that as we move through different sRGB color values, right? We've got a red channel, a green channel, and a blue channel. As we move through different values here, and start at red being equal to 0, green 0, and blue 0. And as we start adding values to these color channels, and we start increasing the brightness of a color, right? The results are actually nonlinear. So you might think that if we add 10. If we add 10, let's say, as an example, to each of our color channels, well, we're going to get some gray value pretty close to black, right? A very dark gray value. You might think that, as we just add values here, that the results would be linear, such that, adding 10, adding 1, adding whatever you like on the dark side of the value spectrum would have a linear relationship. It would be the same linear relationship as what happens with your brighter grays, right? So, if let's actually just move this down a little bit, right? So if we're adding values and operating close to the lower end of the value spectrum, you might expect that whatever relationship between number and value to actually be the same as when we're operating in the upper end of the spectrum here, with values closer to 255, which is the maximum value we can store in a standard 8-bit sRGB image. But that, in fact, is not true. The reason sRGB is a nonlinear color space is because if we were to look at a graph of this being the darker values that we can create, and this end of our x-axis being the lighter values we can create, and of course this being the range of numbers from 0 to 255, right? The values we can store in a standard 8-bit sRGB image, we're going to find that it is not a linear relationship, but rather a nonlinear relationship, something that looks a bit more like this. And this is just because human eyes are way better at differentiating differences in dark values, so values on the darker end of the spectrum, than lighter values, right? So we can see essentially more shades of gray on the darker end and fewer shades of gray on the lighter end. So, well, we might as well just use these integer values, right? The smallest difference between values in 8-bit sRGB is just one integer, right? So we might as well use our integer values to encode a larger range of your darker values and a smaller range, for the same number of integers, actually a smaller range of lighter values, right? So this nonlinear curve is what we're talking about when we talk of nonlinear sRGB. Okay, so that's just a quick overview of how sRGB works. And I mean, really the point here is that this nonlinear set of brightness values is simply inappropriate for encoding something like a high dynamic range image. Not only are we dealing with brightness intensity values outside the range of human vision, but they should all be encoded linearly, not non-linearly. That doesn't make a whole lot of sense. All right, and another issue that we do need to address about normal sRGB images is the fact that they store color information using only 8 bits of information for each color channel, right? So the JPEGs that your camera produces, they are 8-bit sRGB images. And well, of course, all that means is that you only have 8 bits to store an integer value in order to represent either your red, green, or blue channels. So any value from 0000 0000 to 11111111, or in other words, you have a range of values from 0 to 255, or in total 256 or 2 to the 8 possible values that you can store for one color channel. And well, I mean, this is where we run into the issue with just not being able to correctly store all these possible exposure values in a single image, right? Look at what happened, right? Just storing this IBL as an 8-bit. Let's just look at the image mode here in Photoshop. This is an 8 bits per channel image. And of course, there's no way we can store enough brightness values in such a small image. So what we're also going to find is that in most cases we actually use a 32-bit image. We can again look at the image mode in Photoshop here for this high dynamic range image. It is a 32-bit image. It is possible to use 16-bit images as well for IBLs. However, usually we do use 32-bit images. All right, so storing a 32-bit image allows us to correctly store all of the brightness values that we obtain from the scene. And in addition to that, we store the image in a linear color space using either the HDR file format or EXR is another really common one that's used, right? So this one is in the HDR file format. This one is an EXR. Either will work just fine for storing linear color data.